Hi, everyone, and thanks for joining this presentation here. We're going to talk about something slightly different. For the next 20 or so minutes, we're going to talk about digitalization and the digital technologies that are also part of the refrigeration industry. So for the topic today, I posed this fairly abstract question, maybe: are self-maintaining systems the future of refrigeration? And during the next 20 or so minutes, we're going to elaborate on that particular topic. Now, as you can probably see from the logo, I come from Danfoss, so we're one of the equipment manufacturers in the refrigeration industry, but we also provide a number of different softwares for the industry. My name is Thomas Kolster, and I work for the digital services part of Danfoss. So let's get started on it. Just maybe a short disclaimer. I'm not going to talk in very much detail about artificial intelligence or machine learning or IoT or any of those topics, but it is going to be an enabler for this conversation. So let's get started. I'll focus very much on the tangible value that these technologies bring for us. But in order to get started, let's settle on some basics. So the situation as we know it today is probably not news to everybody that the energy prices are going through the roof. It impacts all businesses, and it is potentially life-threatening for some businesses that rely very much on refrigeration. Take food retail, for example, where up to 50% of the energy consumption in a normal food retail store could go to refrigeration or refrigeration-related activities. So when the energy prices increase 4%, it actually has quite a significant impact of the overall profitability of that business. There's also another trend going on where a lot of skilled workers are leaving the industry. So if you look globally, of course, there are global differences. It's very prominent across the pond over in the US, where roughly a third of all skilled technicians are set to leave the market due to retirement within the next 5 or so years. So this actually means that a lot of knowledge is actually leaving the industry as we speak. It's already started, and it's going to roll for another 5 or so years. And it has the impact, of course, that the general knowledge level of technicians servicing refrigeration systems is going to decrease over time. There's simply going to be less people that have the required training and the required knowledge. What is also happening in the industry is a fairly low first-time fix rate. Again, this varies a little bit from industry to industry or sub-industry to sub-industry, system to system, but generally it's a topic. So with these things in mind, let's have a little bit of a closer look into how the digital technologies can support and enable and to a certain extent alleviate some of these problems. But first, let's just talk about maintenance. Let's talk about the costs and the issues related to maintenance. Now, first of all, when we talk about a system failure, it doesn't necessarily have to be a catastrophic system failure. It doesn't have to be a refrigeration system or a compressor that breaks down and doesn't produce the temperature needed. It could also be somewhere in between, meaning that the system is running. The temperature might seem okay in the cases or wherever the temperature is going, but due to certain circumstances in the system requires more energy to run. So it doesn't have to be a binary, either the system is running or it's not running, but it could also be somewhere in between, and that's often where we don't recognize the issue. So system failure doesn't always mean a complete outage. But let's look at the cost breakdown, because this is where it gets a little bit interesting, right? You have the above the line costs. So if you compare it to an iceberg, you have the tip of the iceberg. So what goes above the surface? So these are the maintenance costs. So the truck rolls and the technician's hours that it takes to go and fix a problem. But there are many other costs related that aren't necessarily calculated as part of a system breakdown. So there's the direct costs, as we see here, and then there's the indirect costs that are, so to speak, if we stay in the iceberg analogy, somewhere below the surface. So just to provide a couple of examples, obviously it's not an exhaustive list of costs, but this is taking mainly from a food retail perspective. So if you have a supermarket with a refrigeration issue, you have a lot of hidden costs. You have the store employee time it takes to clear out goods, it takes to detect the issue, to direct the service technician, etc. All the time that goes from actually serving the customers. There's lost sales. There's possibly loss in refrigerant, which is also expensive. There are compliance-related issues. It could even be in some countries legislation if you have a food loss scenario. There is also fines that needs to be paid in case of a food loss scenario. So there are many indirect costs that aren't just related to the actual maintenance costs related to getting the system up and running again. So that's the cost breakdown. And if you just add it all up, what we see is that typically the costs are a factor 5 indirect costs versus direct costs. So the impact of a system failure, whether it's a catastrophic system failure, as I spoke about just before, or it's a failure meaning that the system consumes much more energy because of insufficient settings or whatever that causes a high energy surge, it has a quite significant impact on the costs related to running the system or maintaining the system. Now, maybe to get a little bit back to the topic of self-maintaining systems, then as I mentioned in the beginning, I won't talk in detail about Internet of Things or machine learning or anything of the like, but I am going to talk about, for the next 6 or 7 or so minutes, about connected systems. Because the way I see it, connected systems and having a system that is connected, a system that is recording data or sending data to a cloud or to any other software application where this data can be analyzed and actioned upon, is a very, very important factor, both now and definitely in the future, in order to reduce costs and in order to deal with the fact that there are a lot of skilled workers leaving the industry, as we just established in the first slide. And for that, I'm going to talk specifically about these 4 items you see here on the right-hand side. I'll touch on data and the power of data. We'll talk about prediction. We'll talk about automation. And finally, we'll talk about benchmarking. So let's get started on that. First, we start on data. And most systems actually have quite a lot of data. So if you're running a system that has a Danfoss AdaptCool electronic controller series tied to it, you most likely have hundreds, if not thousands, of different data points already. If, of course, you have 0 electronic controls related to the system, then most likely it's very few data points. But in many cases, we actually see systems that have quite a lot of data already recorded. The problem is the data is just not being properly leveraged to anything. So the data is just sitting there and is not being used. But the power of data is really interesting when you start actually analyzing the data. That's where you can see the value of the data, because the data, if it just sits in a database, it's just numbers. But if you start tying that data into actionable insights, this is where you can really generate a lot more value. And there's one example that I want to highlight here for this case. So that's the example of refrigerant leak detection. Now, one of the things that Danfoss has been working on in the past couple of years is exactly how can we leverage data that already exists in order to provide better insights. And one of the outcomes that came out of that is actually leveraging very few data points, like valve opening degrees and data about refrigerant refills. Because in order to leverage those 2 data points, you could actually feed a machine learning algorithm to detect potential refrigerant leaks. And so far, what we've seen is that with these machine learning algorithm, refrigerant leaks can be detected up to 2 to 3 weeks before any other usual leak detection systems. So it's actually quite significant that by leveraging existing data that's already available. So you don't have to retrofit sensors, you don't have to retrofit any black boxes or any other electronics that goes into the system. You can actually just leverage already existing data and do predictions of potential catastrophic failures 2 to 3 weeks in advance. And obviously the benefit is that you can keep the system running because you detect a problem before it becomes a big problem. But you also basically stop an issue with flash gas, for example, which will cause the system to consume more energy in order to provide the same capacity. There's a lot of benefit, and this is just one of many. Now, another example where we're also talking about just leveraging existing data, but keeping it more general in the topic of predictive maintenance here, is compressors. So compressors are the heart of the system and allows us to record a lot of really valuable data that shows how is the system running today. Right now, right here, it gives us an instant picture of how the system is working. But again, by leveraging this data and creating models, machine learning models and algorithms, we can actually start to predict how the system is going to perform in the future. So how do we do that? Well, what you need to do is you need to build a baseline model. You need to build a model for each compressor rack or each system basically that defines the baseline, that defines what does normal operation look like. When you have a model that defines normal operation, you can put it into action, so to speak. So it keeps in real time analyzing the live data from the system, comparing it with the model that shows what does normal look like, and then it flags outliers before that turns into any catastrophic failure or any other failures. The system basically says, well, here's an operation that is not normal. And when there are so many observations, so we're trying to remove the statistical outliers, the one-off outliers, but when there seems to be a pattern, the software can basically raise a flag and say, hey, there is a prediction that this compressor might fail within a certain amount of weeks, or there is just a prediction that is now running out of what we consider normal operations. So what's the value of that? Well, the value is, again, that you can start smart scheduling maintenance calls. Instead of doing recurring pre-planned maintenance calls, you can start actually doing more reactive maintenance calls based on flags, based on how systems are currently operating. That will reduce costs because you don't have to send technicians to systems that aren't properly, that are working properly. But you would also be able to tell a technician as he or she arrives on site what is actually going on with the system, what is potentially causing the issue. So it's not just a predictive solution, it's also partly a diagnostic solution. Now moving on, talking about benchmarking as the third of the 4 topics. This is extremely relevant if you are somewhat responsible for the operations or maintenance of more than one system. Because many refrigeration systems, most of them are somewhat unique, meaning that if you just look at one data set from one system and compare it with the same data set but from a different system, it's a little bit like comparing apples and oranges. Because the system is unique, so you need to somehow be able to normalize the data in order to benchmark. And why do we want to normalize? Why do we want to benchmark? Well, if you run 100 different systems, again, let's take the food retail example. If you're responsible for the operations of 100 different stores, you would probably want to know, where should I put my focus? Where should I put my maintenance budget this month or this week? Should I go to store A or to store B? Well, when you can compare the performance of the different sites following a uniformed view on the data, then you would actually know which store is performing relative to the other. And that would give you basically a ranking of which stores that require the most attention. Then finally, just a word on automation. And I'm going to speak a little bit broadly about automation, but in this case, I brought the example from smart energy, because automation is basically, in a nutshell, a solution where the system acts on data in real time. Means that there are no human intervention necessary. And of course, there's also a semi-automatic or semi-automated solution where it's somewhere in between, that the system suggests a change, and there can be a human intervention to approve or disapprove the change, so to accept or reject the change. But in this case, let's just talk about automation in general. And the example that I brought here is actually one of the examples that I really, really like. It's from this model that you see here. It's a energy demand trend from 2020 from a energy utility in California. During the wildfires in August in California, there were a significant push on or demand on energy. This was partly due to the fact that the energy supply was disrupted due to wildfires, but also due to the fact that there were a significantly high demand on energy because of many patients were at that time admitted to intensive care units, depending on respirators due to the COVID-19 situation. Now, in order to avoid blackouts, the utility had to do something, and the utility had to somehow figure out a way to reduce demand because just increasing supply wasn't enough. And the way to do that is by making sure that those that consume the energy can reduce their consumption temporarily. And they succeeded by doing so following an automatic demand response program where the utility would basically, typically through an energy aggregator, send a message to those consuming the energy and asking for a temporary reduction, thereby, as you can see here, reducing the actual demand quite significantly compared to the day ahead forecast. And that actually meant that ICUs, intensive care units, could continue to run respirators, and that meant that a lot of lives were actually saved. This is, of course, an extreme example of a special situation, but it is in fact also relevant, especially in today's energy crisis, where energy prices are increasing, and especially in the markets where energy prices fluctuate hour by hour. It's actually possible to pre-program curtailment programs, leveraging stored thermal energy in refrigeration systems in order to curtail compressor operations for 45 minutes or an hour, and thereby reduce quite a lot of peak scenarios, and then push the demand or model the demand according to energy prices. So those are the 4 examples. Then the question, are self-maintaining systems the future of refrigeration? It's not really a hard yes or a hard no. It's somewhere in between, you can say. I definitely think that systems will become smarter and more predictive, and definitely not completely self-maintaining, but they will help technicians and owners of the system to detect when systems are not running very well, and in order to plan better maintenance in the future. So with that being said, thank you so much for your attention.